So basically, our webinar agenda today will be broken down into these items. We will be starting by showing how the thermal comfort and environmental control can be quantified, how they are important in designing our buildings, interior and exteriors of our buildings. What are the key factors to be considered, and what makes a room comfortable? How can we quantify this and evaluate it using not only the design codes that they provide for designing buildings, but also for high fidelity simulations that thermal comfort codes such as SIPSI or Asher 55 needs to comply with. We will be addressing some industry pains, how the usual or the conventional codes used for the HVAC simulations or HVAC assessment or designing systems have some limitations, and there are some items or some parameters that can't be pictured from such simulations. Maybe they are good for a preliminary design phase, but they are not sufficient enough in order to judge this building is energy efficient enough, is mitigating hotspots and bad weather conditions inside. Then we will introduce to the new people that from other fields that they are not familiar with this term computational fluid dynamics. How can we use it for engineering and construction? What are the benefits, which tool we can use, and how which diagnostics or parameters that can we extract from these simulations? And then I will demonstrate some examples and case studies to show how these simulations can have a lot of benefits that can each industry can benefit from. Then I'm listing briefly some added values out of such virtual simulations, and then my colleague will join and start his live demo demonstrating the graphical user interface of our CFD tool, and how to set up the workflow starting from the CAD extracted from CAD software till the post-processing and evaluating the design. So this is a very important issue that how can we define the thermal comfort or environmental control? Some of you basically hear this term for the first time, and some is not. So I will be demonstrating it briefly. So as humans, we spend most of our time indoors. So we engineer such buildings in order to do some functions to shelter us from uncomfortable conditions that we want to avoid in order to do some specific tasks. So in order to handle such buildings or design it in order to be suitable for each activity that we do every day and to the environmental condition that varies seasonally or day by day. So in order to handle such issues, we have to consider the thermal comfort and environmental conditions. So we use typically, for as you can see here in this picture, there are two people sitting in the same room, but but both of them receive the HVAC ventilation or the HVAC cooling system with different response. This one here feels very cold or quite cold, and this one feels too hot. So for the same amount of mass flow rate, maybe the choosing of putting the vents here or the layout of the HVAC system here may not be quite efficient, because we want to homogenize the flow field in this entire room. So in order to for this person to be dynamically enough to move for each point in the room, feels the same, approximately the same condition without feeling uncomfortable. So we should handle this issue. So this is very astonishing for me when I googled it and I was preparing my presentation here, that I found that more than 40% of the global energy demand is consumed for the building and construction sector. So instead of I spend most of the time working for the automotive industry, and there is a lot of hustle there that they want to reduce emissions, the levels of CO2 and the greenhouse emissions, and or with restrict emission regulations and environmental conditions. But this is my first time I found that there is a sector that which is the building and construction that consumes 40% of the global energy demand, which is responsible enough to the global warming and the CO2 level. So in order to to design our HVAC system, to optimize the energy consumption that each building consume each day or each hour, that would accordingly affect the levels of CO2. We have to handle such issues efficiently. How not to over design the system, how to consider all the factors of the human response there, in order to not over design the system and have a much higher probability that the occupants there will be satisfied enough. So, but when we talk about thermal comfort, this is quite vague term to be said. So how can we quantify such parameters there in order to be dealt with and quantified and judge whether this building is bad design or good design? So as a rule of thumb, that our bodies used to function very well as organs and our other parts in the range of temperature between 36 to 80 to 38 degrees Celsius. So in order to function or not to lose consciousness or has some dizzy feeling or not to lose your effective performance there in the room you are is supposed to work in, you have to address such issues. Not only temperature, but we will consider all the influencing parameters that affect these thermal comfort environmental conditions and how can we enhance the HVAC system. So we can break down the factors that affect the thermal comfort for each one to two categories. The first one called the personal factor, which can be broken down into two parts. One is the metabolic rate, which is we will talk about each one of it in each slide accordingly. But briefly, which is the energy that we release from eating some foods or doing some activity. So we release some energy, and this energy radiate to the environment of us. So we have to design our cooling system and our ventilation system in order to handle this metabolic rate based on the number of people in this room and which activities they used to do in such a room. Then the other thing is the closing part, and the closing part, maybe it differs from region to region, differs from culture to culture. So in order to design a building in Europe, they have their traditions in summer, for example, in their closing, and these conditions of this tradition is not applicable for our tradition here in the Middle East, according to our environments and our culture. So we have to consider this as a factors to evaluate our designs. The other one is some environmental conditions. There is the temperature, the air velocity, level of humidity, and thermal radiation. So many standards start to lump these factors into one equation called the BMV, which means the predicted mean vote, which includes or employ all these factors in one equation in order to judge the performance of the HVAC system inside any building or for any weather conditions, how the people sitting there will be satisfied or not. So not to be long there. So in order to handle such issues, so for example, we have 4 vents here, and the amount of velocity that the people sitting there will feel is around 1.8 meter per second, which may be not according to standards and the statistics that gathered from different people in different countries. This value is not suitable and will make you uncomfortable. So this factor should to be considered, and the people sitting here will not feel comfortable anyway. So we have to handle this. And in order to handle such issues in a three-dimensional domain, we can't treat such a room as a lump, as a black box. Just know the cooling load that we need for for this room, and evaluate it using simple calculations or even some codes. This is not enough to do. This may be efficient or suitable for the preliminary design phases, but for the final decision, we need to make sure that these vents are placed in the optimum places, in order not to make someone here feel a huge number of velocity, a large number of velocity, a large magnitude, and the people there not feel cold enough, and the people here not feel that level of humidity is low or something like this. So the first parameter that come across our mind when we talk about thermal comfort is the temperature. And maybe this is correct, but this is not efficient. This is not sufficient to judge the whole picture of the thermal comfort. Because as I mentioned before, that our bodies used to work at around, on average, 37 degrees Celsius. So if we deviate from such a number, we may feel that we lose our concentration, we lose our performance, we may cause us to our death in certain applications. So we need to identify the hot spots and the cold spot, how to homogenize all these flow feed using the same amount of energy consumed for this building. So if the temperature is quite high, when we do some certain activity, we tend to get sweat, and in order to to exchange this heat with the environment has to be low temperature in order to cool down. The environment should have low humidity level in order to able to exchange this heat with the environment and be cooled down, so make me feel comfortable. So this factor should be handled. Some standards do or define some indoor and outdoor conditions for each city, for each country, for each a continent, because depending on the weather, depending on the season, depending on the location this city located in, whether it's a coastal or not a coastal city, the levels of wind there, the level of temperature will differ. So the design of the HVAC system will not be the same. So we have to consider such issues when we design our buildings. The other thing is air velocity, and as I mentioned before, that the air velocity which make you feel somehow comfortable, will range from 0.8 meter per second to 1.2 meter per second. So in certain area, if these values exceed these limits, you may not feel comfortable. And if I want to comply with standards for thermal comfort, that's such as ASHRAE 55, I have to do such simulations to validate and make sure that my design comply and satisfy these kind of requirements. Another factor to be considered for the airspeed, that the more you increase the airspeed, the more noise you get generated. And for some applications, you can't exceed certain level of applications. For example, maybe for certain buildings, the maximum you can approach is, or asymptote is on average 35 decibel. But for some applications, such as hospitals, surgical room, and some other applications, maybe this is not acceptable there. So we have to handle this acoustic issue or acoustic problem in our design as well. So the third factor that to be considered is the humidity. And when we talk about humidity, we talk about the amount of air the amount of the amount of moisture that the air around us could hold at certain temperature and the pressure. So this kind of humidity level will affect our feel of comfortable, how you feel to be comfortable or not inside certain area. Because as a rule of thumb, you can withstand, or you can feel comfortable for with a relative humidity varies from 30% to 50%. But if it increases or exceeds such thing, you not only feel uncomfortable, but it will affect your interior design, something like this. this area affected, or this painting on the wall affected by the absorption or much humidity in the room. So these factors you have to consider, because it will cost you a lot to retrieve or rework such issues, and maybe affect other kinds of structural elements that you have inside your office or inside your home. So another thing to be considered is that conventional codes can't handle properly that the radiant temperature. And when we talk about the radiant temperature, we talk that the environment inside certain room is quite dynamic, and you can't assume that the radiant temperature can be equal to the dry bulb temperature only, because maybe you change from one activity to another, the energy you release is more, the angles, or the way that the sun shine every day, and go back every day with short wave and long wave radiations. This would vary a lot. How many people inside this room at this instant of time, where exactly they are located inside the room, whether they are located in the middle of the room or in some corners. I want to make sure, I want to make this design very efficient with lower energy consumed. I want to make the flow field quite homogeneous inside this room, in order not to, for certain people, they will go to the thermostat and lower the value of the HVAC system, the cooling system, and this may, increase the energy consumption. And you can avoid this mistake or avoid this issue by only considering doing 3D simulations to handle such issues. Another thing that we mentioned is the metabolic rate. So the amount of energy that you consume and release for each activity differs. So the design that we do for a gymnastic area, for example, will differ from a classroom, will differ from a mosque, will differ from the type of place that we are designing, and the type of people doing certain activities there. So maybe it doesn't differ a lot from being a male or female, but differs quietly significant from sitting or reading to doing some exercises or running there. So as you may see here, that the amount of energy released from your radiant heat will increase. So maybe if you design your HVAC system for a sitting people, this will not be suitable for such people, and they will feel sweat and uncomfortable in your design. The very important thing that we mentioned is the clothing. So we have to consider it based on the country or the city that we are designing this room in, and the culture of people of clothing there, which kind of clothing is preferred to in such time of the year, on such time of the season. So we have to consider. So maybe this book is quite important to handle or to know such factors. The final thing is to be looking at for such judging your design is what I mentioned, that the BMV or the predicted mean vote. This factor, as you may see here, includes all the influencing factors that influence or has impact on the thermal comfort of each person. So in this single equation, we can predict how much people are probably satisfied with our design or not. So as a rule of thumb, we have to be in this regime to be from negative 0.3 to 0.3 as a maximum. So this is the region to comply with thermal comfort standards such as ASHRAE 55. Beyond this region, you will feel when we go to the right, we feel warm and hot, and when we go to the left, we will feel cold. So the best scenario is to be 0, but can't be achieved as an easy task. But anyways, we can, for this application, we have some hot spots or red spots here that suffer from cold regions. So maybe the people sitting there will not feel comfortable enough. Maybe the only thing we have to need not to change the HVAC system, but we change the orientation or the layout, or how many of them we can use there. So this is very important to be satisfied. And this is on the vertical axis, the percentage, predicted percentage of dissatisfied people. So when we are around the zero mean, we are less than 7% of the people inside this room would feel dissatisfied. So we can say that 93% of the people inside there will feel satisfied. So this is very good. So usually people or staff working in the HVAC or civil and architecture engineering use some simple calculations, rough estimates, and codes such as HAB software. So they used to evaluate the cooling load for each room. How can I allocate certain vents and pipes and connections and something like this. But there is always a trade-off between, or a tension between, the design codes that buildings employ or imply or needs such engineers to do, and what actually people experience. So the problem with these codes, they don't see actually the 3D space inside such a room. What is the dynamic environment that could happen there based on the number of people sitting there, which activities they used to do. So we have to, picture such 3Dness or three-dimensionality of the physical problem in order to perfectly judge whether this experience of such a system that I redesigned would be suitable for certain people or not. So maybe these design codes can be beneficial for the preliminary phase, but can't be relied on for the final decision. So as I mentioned, that the environment in a certain room or a certain building is quite dynamic. So we have to consider it. This is a reality, to be frankly speaking. So we have to know the limitation of our assumptions. I don't mind at all to use certain equations, but in order to judge it well, not to use it beyond the limitation of it, and try to to normalize its value and say it can work in any domain or in any temperature range. So this is not accurate, and this is very important issues that 97% of the people working there never know that there is standards that handle such a problem, which called thermal environment or thermal comfort conditions. So, and some of them not, and the rest of the 3% that they know this standard, 1.5% of them only know how to use such standard. So in order to eliminate such illiteracy in such a field, we have to know such that there is standards for thermal comfort, there is a computational fluid dynamics to be done there in order to validate our design. So actually, what is actually CFD? So CFD stands for computational fluid dynamics. So what is computational fluid dynamics? So for the people not experienced it or not studied this before, in computational fluid dynamics we use the fluid flow equations to model such environmental conditions such as conservation of mass, momentum, energy equations, and so on. Deal with complex geometries, different scenarios from steady to transient states, the daylight, time variation, so on. How to picture this reading? This can't be, these kinds of visualization and judgment of the flow field inside the theater, for example, can't be judged only from certain calculations that do some mass balance on the inlets and outlets. This cannot be pictured for this code, and you have to employ some 3D code to visualize each point inside this room or this theater, how it function well according to the thermal comfort standard. This is other applications that can be used. That say CFD can be used there. This is an automotive industry, and this is the aerospace. So using CFD, we can evaluate that such parameters that standards require to comply with, such as supply and return temperature, relative humidity, solar radiation, and doing such analysis based on steady or transient analysis. So we need CFD in general in order to predict the performance of certain design, not only in the architecture, but in any engineering field, and how can we optimize such design in order to fit our requirements with the minimal cost. And here is the cost. The cost here will, will be can be broken down into some elements. Some where the environment will pay, which is the CO2 levels that we have to reduce, because as you may know, in this day and age, we suffer a lot from the climatic change and unprecedented floods in certain areas, especially in Europe, and unprecedented fires in the forest in the Middle East area, and in South America. So we have to pay great attention to the environmental costs that we all pay together, not only the designer or the manufacturer or something like this. So this is one, and the other one is when people sitting or hire a certain area or certain flat apartment or something like this, they pay for the electricity. So if you not design the windows quite efficient, if you not designing the HVAC system for certain office, they will pay a lot to the governments to pay for such electricity, and they pay a lot for these over-designed devices without any gain in the performance or the uncomfort or the comfortable levels they feel inside such buildings. So we have to do this using 3D simulations in order also to optimize and minimize energy consumed. So usually people for architecture, engineering, and construction field use CFD to examine or evaluate certain performance, such as these factors, in order to validate their HVAC system and part to predict the wind load. Because if we want to, for example, if we want to estimate the airflow for a complete city and a pollution, to test the flood area, in order to study the daylight and solar radiation, we can do such large scales and three-dimensionality of the physical problem using only some rough calculations or one-dimensional codes. Another thing that we should handle, the look forward to, is to improve the energy efficiency for this building for the consideration that we mentioned earlier. How can we eliminate such disease infection or infection spread? How can estimate how the fire can propagate in a catastrophic scenario? Which is the resident time in order to evacuate such people in a certain time? So this is an example for test the infection spread for the COVID-19 or the coronavirus. How can our mask can prevent us? These calculations can't be done using paper and hand. This should be done in three-dimensional simulations. And this is of course, how can we predict the noise levels in the ducts? This can't be handled by the simplified codes. This kind of noise level we can avoid by only modifying a little bit in our design and have a great impact on our performance. So there are some other applications. The important one for me here is that we have to do the trade-off between the natural convection and the mechanical ventilation, because natural convection is natural, so we can depend on it without paying any cost for it, additional cost for it. But the mechanical ventilation, on the other hand, we pay for it. The environment pays for it, so we have to do such a game in a very wise way. So why specifically SStream? SStream is a CFD tool that MSC Software has, and it's a Japanese tool developed especially for the automotive market and the Japanese market, and it's widely used there. And for some people who know how the automotive industry that the Japanese car are located in, they know that they are very efficient and they have their reputation in the marketplace. So this software is used by 97% of the automotive market in Japan. So this software is quite efficient, but this kind of module is quite oriented to the architectural and construction engineering, because maybe as a mechanical engineer or as an aerospace engineer, I am quite expert with the parameters, with the numerical values that I should input to the code and doing with the hassles everywhere. But for civil engineers, architecture, they don't have such strong backgrounds using these partial differential equations, use or handle such code. So this privilege is very beneficial for them because using this software you can you get benefit from the wizard workflow because you can move choose whether you want to solve for an external aerodynamics or interior aerodynamics, whether you want to choose to solve the heat equations or radiation or not, whether you want the laminar flow or turbulent flow, whether you want to solve atmospheric boundary layer or not. These kind of wizards saves a lot of time from you in order to do such simulations. So I'm not don't or doesn't need actually an expert to deal with it. So it can be taught within 2 or 3 days at all. So you can start your simulation and do it in a couple of minutes. So this is a very important one. We have a lot of customers worldwide. So very important issue for some people who do modeling, and some who didn't know before is first is you have to deal with the CAD out of CAD software, and you have to to customize it in order to do certain simulation, whether you want to do CFD simulation or you want to do structure analysis. Some features are important here and some features are important there, so you have to tweak your geometry a little bit. So this consumes some time, but here in SC Stream you don't have to do this. You can use the level of the featuring to the CAD details that you need. So for example, for this gap between two parts, you don't want to deal with the CAD software to eliminate it, and you don't want to capture it in your simulation. So you can choose from certain parameters in the code that you can fill this gap automatically and don't deal with it. So this saves a lot of time on the CAD level, on pre-processing level, and on the meshing or discretizing level. So the very important aspect here that we should it's worth mentioning that for general CFD tools, that various companies has worldwide, in order to do such CFD simulation, you have to extract these kind of drafts and convert it usually to 3D, and with a lot of details and a lot of cleaning or defeaturing some details that you don't want to simulate, and then import it to the CAD. And this consumed a lot of time from engineers who don't actually experience it in this field. And for civil engineers or architecture engineers, they usually deal with certain software such as Revit or or AutoCAD or some 2D drafts. But in order to convert these 2D drafts or planes to 3D geometries, it would take a lot, from them. So in order to ease these functionalities or ease these tasks for civil engineers and architectures that they are not experienced enough for this, there is a plugin tool for this software that enables you extract automatically the CAD from the Revit, for example, or AutoCAD directly to SC Stream to analyze your model without any hassle in between. So this saves a lot of time doing some CAD stuff. So we can comply with various extensions and complying with different software that civil and architecture engineers use every day with different extensions. So we can, this is a privilege that MSC provides that.
Amr, I'm sorry for the disruption, but apparently for some mistakes that happened, you're out of the shared screen. So can you please reshare your screen?
Okay.
Sorry for the disruption. Thank you.
Okay, can you see it now?
Yeah, now it's good. I'm sorry. Yeah, you can continue, please. Thank you.
Okay, perfect. Okay, the another thing that is that MSC provides that it has a wide portfolio that can handle each aspect of engineering problems, dealing from computational fluid dynamics, finite element structure analysis, acoustics, manufacturing, and so on. So how can we integrate such data inside certain buildings to evaluate the wind loads on the exterior building? How can we assess it from a structure point of view? How can we evaluate our interior design? Of the building there and shift it back and so on. So these kind of simulation or animations come out from the software that I mentioned, so it help you a lot. This is another example to that the how can we use it to emerge or evaluate how an airport can be immersed with a flood. How can the our designs can be can be suitably designed because not to be immersed a lot or losing some a lot of damage there. So this is another example doing a certain stadium here, a flow field there with a massively parallel code. In order to accelerate your design, accelerate your simulation, you have to use a very powerful hardware. But using MSC SC Stream, it's a very scalable software, so it can scale up to thousands of cores. And recently they do a benchmark problem in the fastest supercomputer in the world, located in Japan, and it took around 100,000 cores to that scale up and do very complex grids resolution in a couple of hours. So this will help you a lot to evaluate your designs in a couple of minutes or couple of hours to make the right decision. This is an example for the virtual reality and augmented reality that the software can provide for the pre-processing. This is the building inside the building of Hexagon. So using the 3D simulation, you can picture and visualize using augmented reality tools. So this is a very powerful post-processing tool to be used. So before coming to the live demo, I want to mention the added values using such tools. So using such tools, you can go beyond the limitations of the design codes that used in each for buildings. In architecture and civil engineering, you can predict the flow, direction, and magnitude precisely. You can evaluate your energy efficiency and detect the hotspots, and not to over design your system, and how to optimize the energy consumption there, how to comply, which is a very important issue with the international standards. How can you make the right decision based on high fidelity results, not only simple equations, and how can you do the trade-off actually between the natural convection and the forced convection. So I will let my colleague to continue his to demonstrate his live demo here. Abdulkarim, you can start from your side.
Okay, thanks my colleague and friend Amr. Hello, everyone. Hello, everyone. Okay. Okay, thanks, my colleague and friend Amr and Hussam. Hello, everyone. My name is Mohammed Abdelkrim, and I'm technical application engineer. I'm responsible for integrating live applications and model it using our MSC products. Well, let's get to the point straight. I'm going to shed light on the technicalities on how to initialize and set up your model, CAD or whatever your model is using EC and how to get some colorful results and fancy images using during the post-process stage in a couple of minutes. So let's get started. Could you confirm, please, when you see my screen?
Yes, I see it.
Confirmed.
Okay, in our program here we have three different models with the same dimensions. It's about office with some obstacle inside it, and we have some people, as you can see. This office contain in the first design layout, we can see we have two openings, one for inlet and the second for outlet. In the other two design layouts, we changed the position of the inlet. By the way, the inlet is the red panel and the outlet is the black panel. And also in the third design layout, we increase the number of inlets and just change the position of these panels to show how the position of inlets and outlets and their numbers and dimension can affect our results. Nearly all the designs have the same inlet and outlet conditions. As you can see, I have here in the first design layout, the dimension of the inlet is 1 by 1 meter, the dimension outlet, and also the initial domain temperature and inlet and outlet condition. We just fixed the mesh elements to show the results when will be changed. It's about the changing the position of the inlet and outlet. So let's get to the program. When you start the program, it's simple and easy. You can import your CAD data. As when you begin, it have this layout. Here you can import your CAD file here, and here you can change its name. This is where you can save your file, and this is a library if you have library. Here when I import the CAD file, you can import the CAD file with different extensions. One of them is Parasolid, which is widely used. Also, you can import different extensions either from CATIA, SolidWorks, Inventor, 3D Max, Autodesk, Revit. Even you can, there is an add-in where you can plug in your program, and it will import the file directly to the AC stream, and you can initiate your model. Here you can just change the scale and the dimensions or the origin of your model. You can either change the computational domain of your model. Here you can see you can also change the units that you use in your setup. Here the analysis type, you can change flow analysis, flow type, heat if you want to consider heat or not, solar radiation if you are dealing with a problem that contains solar radiation. Also in your turbulence model, you can choose a model that will solve your system of equations. This is also the point where you can change the temperature of your domain or the parts that is contained in your domain. Also you can change your the type of computational domain where you can solve your problem. Here in external flow, we can deal with buildings. In external flow, forced convection, if there is forced convection or natural convection. If you're dealing with problems that contains heat, you will choose to solve it using internal flow, heat enclosure, heat release. And each one of these setups, there is another setup that you can use it. Here in internal flow, you determine the enclosure boundaries that contain your domain. So this will be your domain. Once again, I forgot to say that here you can change also the dimensions of your computational domain. As you can see, when I just change dimensions such that and preview, you can see that it will be changed as you like. That's it. Also in your to set up your initial your inlet and outlet vents, you can use one of these shapes here if you are dealing with 3D parts, and here if you are dealing with 2D parts. You can also change their location and size. Okay, let me see. Let me get here is a different model with determined computational domain. Here after we fixed our inlet and outlet vents, we just go to condition wizard. Here you can set up your whole problem using type of flow inlet, flow outlet, your boundary condition. So in analysis type, you can choose your flow either to be laminar or turbulent. In analysis types, there is various types where you can solve heat problem, radiation problem, humidity, ventilation, air conditioning. Either you can solve for moving objects and solidification and melting problem. In the flow boundary condition, you once you register your inlet and outlet condition, you can put any condition using one of these options. As you can see here, I have different condition times, fixed velocity, fixed flow rate, radial flow rate. What each one of them has its determined or predetermined object. Also here in wall boundary condition, you can see that you have various wall boundary condition such as free slip, no slip. In the thermal boundary condition, since you determine that you will solve for enclosure heat, it will automatically specify its domain, as you can see here, its domain here, as they are the enclosure where where it will solve the air that is contained in this domain. Symmetrical boundary is used for problems that contain symmetry planes. Source condition also if you have source of smoke in firefighting problems. Also fixed condition if you have fixed condition such as fixed temperature. Ventilation efficiency, it is used to determine the age of air and life of expectancy of air. Analysis control, here you can determine the number of cycles and the convergence criteria in your problem. As you can see, the setup method is nearly simple without any complications. You can set up your model within few minutes and just get your results immediately. When you if you want to execute your solver, you just press the execute solver, and when it start to solve your problem, it's matter of minutes and seconds to obtain your result. When you finish, when the solver finish, you can see here an L file. It says all the information you can need, like time, the total time it took to solve this problem, and number of cycles that the problem used to reach the final steady state. Also, you can see here some numbers that is represent your pressure, the dynamic pressure, Selman energy density. These values can be handful in further calculations. Let me get through the post process. As you can see here, when you get your when you get your model, it will be something like that. To get some contour, as you can see here, you have plan. In the coordinate, you can change your plan where you can see your results, either x-axis or y-axis or z-axis. Also, you can choose the variables that you want to see from here. As you can see, either temperature, if you want to see temperature, if you want to see magnitude of velocity, if you want to see age of air, remainder of air. Let me speak about age of air in few lines. Age of air it's about air change efficiency contained within species. It also allows the connection between the path and development of each moving air particle inside the domain. So when you get a red region like that, you can see that, by the way, this is the result of the second design layout. As you can see here, the age of air here is nearly high at the corners and in the middle, which means that maybe the people in this region may feel discomfort since the air isn't moving or circulated enough in this area. Also, as you can see from the first design layout, let me show it to you. Also, as you can see here, the age of air nearly changed. and yet there's some spots where the air is not well circulated. But if you see here in this plane, I can see that. Let me show it to you. Edge of air here. As you can see here, the edge of air is nearly fresh. As you can see, it may be well circulated. The air, it is a good indicator that the air is well circulated in this area. That's by changing the position of vents. That's why the CFD is considered to be important in such cases. Also, you can see the life expectancy of air by choosing remainder of air. It shows how much or the volume rate of air that could be displaced or may stay in a certain place in the model for a long time with respect to other spots in the model. So as you can see here, it is nearly fresh, but here it may stay a lot. In the second design layout, also, as you can see, nothing changed, but in the third design layout, you can see that you can see here you can see that it's nearly changeable here, but just the air may be staying in these spots for a while. So the circulation or ventilation of air or efficiency of air can be determined using edge of air. Also, you can see the distribution of temperature here is nearly uniform in the whole place. Nobody will feel discomfort. While here you can see that some places is not doesn't contain same temperature. Some people may feel cold or hot. Also, you can see that you can get your velocity vectors in this model. You can see that the air is nearly well circulated in this region. You can also use streamlines which shows us the trajectory of the air in the room. So if we hide this, let's see if we, as you can see, the air nearly is well circulated in this domain. Nearly no spot contains constant or stopping air, but here you can see that it's nearly, in some places it's barely moving, such as this place, and you can see that it has high concentration movement in this area. So something like that, I don't think you can get it using other program or simulation program without taking into consideration the analysis of CFD. Also, you can export your results in various ways. As you can see here, you can import either in photo with two different formats, GBG and PMB. Also, you can, if you want to export a short video, you can use either AVI or WMV. You have one good quality export and little or bad quality. So it's a matter of minutes or seconds. As you can see, you just determine the place where you want to save your problem, and then just click start and animation. Here it will record for few seconds, and then you can just press on end, and you will get something like that. demonstrating your short video animation. Also, you can get PMV, which is considered to be important in architecture, engineering, and ventilation. Here in extended variables, you can get PMV, predicted mean vote, but since we don't solve for humidity and radiation problem, you won't get it. But when you consider humidity and radiation in this in your analysis, you can get the values of BMV, which will be useful in your design, interior design of the room. That's it. So as you can see here, from just three different layouts, three different design layouts. The first one took 15 minutes, the second 9 minutes, third 3 minutes. As you can see, the number of cycles also decreasing in your computation time, since your problem is nearly symmetric. Here I can solve for quarter of the domain of my domain, so you will have less time computation. Also, as you can see here, the temperature distribution is nearly uniform in this area, but in these two design layouts, it may be not efficient enough. Also, for velocity distribution, it's here is well circulated, but in these two areas, some people may feel discomfort due to the head of the column of air above their heads, and so they don't feel comfortable with this. Also, the edge of air, as we talk about, the efficiency of changing the air in your circulated area. As you can see here in the design layout, it is continuously changed, while in the first two design layouts, there are some places where the air is still in its spot. Also, as you can see here, streamlines. It is well circulated here, while the first two design layouts, maybe the inlet and outlet vents, the position of inlet and outlet vents is not suitable in these places. Such conclusion you can get it from using or get it without considering the CFD analysis in your study, and just shows that CFD is crucial in your study during your design of an office room. That's it. I hope that the demo was quite and simple. Does anybody have questions? Do anybody have questions?